Hey folks, let's go over the explanation to the solutions for this circuit's assessment. So first one says a total of 10 coulombs of charge flows through a circuit in 30 seconds. If the circuit was powered by a 10-volt power supply, what is the resistance of the circuit? So first thing to know or to remember is that if I tell you 10 coulombs of charge in 30 seconds, that allows you to find current because amps is in coulombs per second. So if you take the 10 coulombs and you divide it by 30 seconds, you're going to get the current. And that ends up being 1/3 of an amp. Okay, and now you want to find the resistance of the circuit, and R is equal to V divided by I. So V divided by I. And we know the voltage, it's 10 volts. We know the current, it's 1/3 of an amp. So you do 10 divided by 1/3, which should give you 30. So 30 ohms would be the solution. Okay, part B. If the circuit was powered by a 10-volt power supply, how much energy was dissipated by the circuit? Energy is in joules. That's what we're looking for. A volt is a joule per coulomb. So joules per coulomb times coulombs is just going to give us joules, which is what we want. So joules per coulomb, that's volts. Volts times amount of charge. So you literally just have to take the 10 volts times the 10 coulombs of charge, and you get 100 joules. And then part C, if the circuit was powered using a 10-volt power supply, what was the power in the circuit? So there's a bunch of different ways you can find this. We actually happen to already know, so you have to know that power is joules per second, or watts if you prefer. And there's a bunch of different ways you can find it. You can find it by doing V times I. You can do it by doing I squared R or V squared over R. But in this case, we already have the information we need to do it just by the definition of a watt, which is it's joules, a joule per second. And we know from the previous part that it was 100 joules that was dissipated in 30 seconds. So that means the answer is like 3.33 watts, or 3 1/3 watts, or whatever. Okay, on to part 2. So number 2 says the current supplied to a circuit by a dying battery in its last minute of life is defined by current as a function of time is -1/10 t plus 6 amps. Probably somewhere I should have specified to use seconds, but that's pretty standard. We usually use seconds, although it did say a minute here. Physics, our SI unit is seconds. So what you need to do, basically, because, well, if you were fumbling around wondering what to do, if you use time 0, then this term here is 0, and you realize that at time 0 there's 6 amps of current. And then if you type in 60, as in 60 seconds, or 1 minute later, 60 times -1/10 is -6, plus 6 amps is 0. So that's why the last minute. Basically, the current decreases linearly to 0. You could have graphed it, I guess, if you wanted to, where you had time on the x-axis, and on the y-axis you had current. But remember, current amps is in coulombs per second, and time is in seconds. So each unit of area on this graph is a second times a coulomb per second, which is just a coulomb. So what that's really telling us is we need to, and if you go ahead and graph the thing, like I said, it would go from 6 to 0 over the course of 60 seconds. So what this means is we have to add up all the area under the curve, which, in other words, we're integrating it. So really, you're just integrating from time 0 seconds to time 60 seconds, and you are integrating -1/10 t plus 6, and with respect to time, so it's dt. Okay. If you, I think, if you integrate it correctly, you're going to get -1/20th t squared plus 6t, and then you're going to evaluate that from 0 to 60. So basically plug in 60 for both t's, subtract, and then sum that all up, subtract, putting in 0 for 6 for both t's. If you put in 0 for both t's, you just get 0. So really you're just evaluating at 60 and you're done. So 60 squared, I think you get like -180 for this term, and then plus 360 for this term, which adds up to 180 coulombs. Okay, number 3. We want to know, so a 15 amp copper fuse basically means that if you put more than 15 amps through it, it's going to melt. So how big a voltage can this fuse stand before it melts? Well, what we're really asking is, let's see here. We want to know the voltage that's going to be required to get 15 amps times the resistance of the thing. There we go. So really, I mean, if we know, yeah, okay. So what we're really, the question is intended to make you find R using the formula for the dimensions of the resistor plus the resistivity. So rho times L divided by cross-sectional area. And that'll give you R, and then if you multiply it by the 15 amps, you get your answer. So rho is the 1.7 times 10 to the minus 8th. Length is 0.01 meters. And then A, of course, is pi r squared. You just have to remember that I gave you diameter, so you have to divide it by 2. Also, it's in millimeters, so you have to divide that by 1,000. That might be where you went wrong if you went wrong. Okay. Next part. So, which resistors will experience the same voltage drop? This one, you know what, I'm going to change colors here. I think I just changed colors. We're about to find out, though. There we go. Okay. Which resistors experience the same voltage drop? This one and this one. Because they're in parallel. They experience the same voltage drop as these two together, but not either one of them. And then the resistor at the top, resistor at the bottom were a different, would have been different voltages as well. Okay, the pairs of currents that will be the same, but forget about IT. Well, the combined current also is here and here. So those two will be the same. Also, these two have the same voltage drop across them because they're in parallel, and also they have the same resistance, so they'll have the same current. And then everywhere through this branch has to have the same current because they're all, those effectively are in series with each other. So 1 and 6 have the same current, 2 and 3, and also 4 and 5. There's 3 pairs. All right, 2 combos of voltage that add up to VT. V1, V2, and V6 works because you've made it around the loop. V1, V3, and V6 works, and also V1, V4, V5, and V6 works. You just have to basically go around the loop. And then one combination of currents that adds up to IT. So IT, basically have to add up the 3 branches all together because it's together at R1, it's together at R6. Excuse me, so you have to add up the 3 branches. So that'd be I2 plus I3 plus either I4 or I5 because those are the same. Okie doke. Next part. So the way to do this is first combine, this is the combined resistance. I would do combined resistance first. 4 and 6 is 10. And then you do 1/10 plus 1/6 plus 1/6 and take the reciprocal. And that gives you the combined resistance of that parallel branch. I don't remember what that is right offhand. But then you add that to 3 and add that to 2 and done. And the total resistance ends up being like 7.3 ohms. From here, it actually gets fairly easy. It's just sort of a logic puzzle. because if you have 12 volts, 7.3 ohms, you can just do V over R, and you know the total current is equal to I'm looking at 1.64 amps, 1.64, and then that will be the same as both I1 here and I6 here. I'm not going to do it right now because I hate trying to draw things with a mouse. Then, when you have those, you can do 2 times this value to get this value, and 3 times this value to get this value. So now you've got V1 and you've got V6. And you can subtract those from the total voltage to get the voltage across 2 and 3. So, and that which will be the same. Once again, when you have the voltage here and the voltage here, you can subtract them from the voltage here, and then you're left with the voltage between this node and this node right there. So that'll give you R2 and R3. So that's, sorry, V2 and V3. So now you've got that one and you've got that one. You can take that, divide by 6 in both of those cases to get that current. And then you're left with just this, this last one here. So you know they have a combined resistance of 10. So you can take that same voltage, V2, V3, and V4 and 5, all the way across 4 and 5. So whatever V2 and V3 were, you can divide it by 10, and that will give you the current in both through both 4 and 5 together, which you've got there and there. And then you can just take R times I, and you'll have this and this. And as a sanity check, you could use numbers 4 through 7 as a sanity check. You would know that, for example, V4 and V5 have to add up to either V2 or V3. And that you would know the current through 4 and 5 plus the current through 3 plus the current through 2 has to add up to the current through 1 and 6. So there's some sanity checks you could have done there. All right. Next page. Oh, I think we're on to the multiple choice now. I'll just go in the order they are. So this one, I'm just going to draw it like you could draw it if you weren't from the College Board, and it would look like this. Let's see. So battery, and then you've got one parallel branch by itself, and then one resistor here. Okay. The resistor here, the one that I'm waggling the mouse around next to, is the resistor here. And then the resistor here is the one that's here. So these other ones are sort of all their own branch that are in parallel with this one. So that's one branch, and the other one includes all of these resistors. So it looks sort of like this. Okay. That one I drew is this one right here. Now you go back through that, and there's another branch, and one of those branches has one resistor on it. That's this one. And then one of those branches has 2 resistors on it. Yeah. There. That's the other branch. So knowing that, now you take those two and do the parallel sum, add them to that, because those two are in series, then add that in parallel with this one, then add that in series with this one, and there you've got the total resistance. And then you can just take 12 volts, divide by that total resistance, and you will get the current, the total current, which is the same in R because it's basically, there's no branches between that and the battery. So that was just a matter of drawing it the right way, or drawing it in a way they could understand. Okay, this one. This one, it wasn't immediately obvious, but those 3 resistors are actually all in parallel. Once again, it was drawn kind of strangely, but look, you can draw a loop through this one without hitting any of the others. You can draw a loop through this one without hitting any of the others, and you can draw a loop through this one without hitting any of the others. So those really are just in parallel. It's just that there's one big old node. That's a node. And the other node is here. But they're all in parallel. Okay, so knowing that, so let's see here. If you know that in this this branch here, there's I coming in, and then this is 2R, and then this is R. That means twice as much current is going to go through here as through here. Half the resistance, R versus 2R, so twice the current. So that means this branch is going to have basically 2/3 I, and this one is going to have 1/3 I. All right. Now, coming into this node, remember, all the currents in and out of a junction always have to be the same. Now, coming into this node, we have 2/3 I from here, and going out, we have 2I. So this must be 1 1/3 I. Like that. So because this is getting more of the current than any of the other ones, we know it has the lowest resistance out of any of them. So I'm trying to remember where I proceeded from here. Basically, I guess if this is 2/3 and this is 1 1/3, which is effectively 4/3, because this has twice the current of this, it must be half the resistance, and so there is the answer ought to be R/2. Well, before I go that, once again, this would have been a lot simpler probably if you had just, might have been simpler if you had drawn them all in parallel, like in a more reasonable configuration. Okay, here's 4 circuits. They want to know which one draws the most power and which one draws the least power. The one that draws the most power is going to be the one that has the lowest resistance. That's this one, most power. The one that draws the least power is the one with the highest resistance. That's this one, because it has two resistors in series. So whichever answer says this one is the most power and this 4 is the most power, 3 is the least. So that's why the answer is E. 4 is the most power, 3 is the least. Okay, and lastly, this one, we have our circuit here, and we have an internal resistance here of 1. Let's see what the first thing they want to know. They want to know, basically just, rank the voltages. Fine. Well, one thing is that R2 and R3 are in parallel because, they're in parallel. So they have the same voltage. So right away, we can narrow it down to D and E because they say V2 is V3. If you go ahead and find the combined resistance of a 12 ohm and a 6 ohm, it's 4. It's 4 ohms. So that means the biggest voltage drop is going to be the 8 ohm resistor, followed by the 4 ohm resistor, followed by the 2 ohm resistor. So the answer should be, let's see, V1 should be the biggest. So the answer is D. Okie doke. And then the last one here wants us to find how much energy is dissipated by the battery's internal resistance in 60 seconds. So remember, energy once again is in joules. Joules. And a volt is a joule per coulomb. So basically, if we knew, let's see here. Yeah, we want to know the voltage in that resistor, that one, because that's joules per coulomb. Then we need to know how many coulombs went through it in 60 seconds. So joules per coulomb times, let's see, joules per coulomb times coulombs is what we want to do. So coulombs, to find how many coulombs in 60 seconds, we're going to need to find the current, because that's in coulombs per second. So the current in coulombs per second times 60 seconds will give us coulombs. We multiply by that by the voltage right here in this one particular resistor, and then we're done. So I think probably, let's see here, do the combined resistance of the whole thing, and you can find the current. 4 plus 8 is 12. Wait, 8, 12, 15. Okay, the total resistance, our total, is 15 ohms. So that means the current, the I total, is just 45 volts divided by 15, so it's 3 amps of current. Okay, so this 3 amps of current times 60 seconds tells us that this number, this is going to be 180 coulombs, is going to go, coulombs of charge is going to go through that resistor in 1 minute. Now we just need how much voltage is dissipated there. Well, it's 1/15 of 45. So, is that right? 1/15 of 45, which is 3. Yeah. So the reason I said that is because the total resistance is 15 ohms. This is 1 ohm, so it'll get one, if being, it says 1/15 of the resistance, it'll get 1/15 of the voltage. So 1/15 of 45 is 3. So this is going to be, this term is going to be 3 volts. So 3 volts times 180 gives you 540 joules. And that's all. All right. I'm going to have you read and or watch some stuff about capacitors and maybe try a couple simple capacitor questions, and then I will see you all on Thursday.